which has very interesting properties in a two-dimensional gas of electron, and you have things happening at the boundaries of this system. But more recently, we also know that holography and black holes are a good example of very interesting physics happening at this edge. And even more recently, this corner proposal, which was, it's an approach to gravity, and in particular, quantum gravity, that was launched based on this paper of 2016 by Fred and Donnelly, which basically takes the boundary as everything that's important in gravity. And these edge modes that we're going to talk about today are also believed to be very important in the understanding of quantum gravity. So we know that boundaries are very important in gauge theories, and that's why we want to study them. Then more precisely for our review paper, we wanted to no.
Okay, I understand what's happening.
Yeah.
We should go back to the presentation.
Oh, I lost the.
Because of press dragon. So
okay, yeah.
Dragon.
It's okay. It was perfect. Thank you. So we first wanted to clarify this, the justification of the presence of edge modes in these theories, because we actually found out that we have, in our treatment, we have a slightly different way of justifying why edge modes need to be present from this Donnelly and Fredé work that I'm going to talk about a bit later. So that was our first goal. Then we also wanted to clarify the role of these edge modes, because as it turns out, there are different types of edge modes, notably in Yang-Mills theory and in gravity. Those two edge modes have different purposes. And so that's something that we also thought was not made really clear in the literature. So that's another thing I'm going to talk about that I think we made a bit clearer. And lastly, but importantly, it turns out that a lot of the literature on the subject is shrouded in a very abstract and advanced mathematical framework that we actually found that was not necessary, like it was not necessary to have such an advanced mathematical language to at least get the main ideas across. So one of the main ideas of the review paper is to present everything in a simple mathematical language to make this whole subject more accessible to a broader part of the community.
So my understanding is that you guys learn the stuff and now you organize.
Yes, exactly. Like we try to understand this paper. That's exactly. And then we thought that the work that we did to understand this could be useful for other people as well that wanted to learn this thing. Okay, so let me start with this covariant phase space formalism. So this is a formalism that was elaborated first in the late 70s, but the modern framework, the modern formulation that people know about is based on the work of Eyerly, Ward, and Zupas. So it is based on the mathematical framework of Anderson's variational bicomplex, if that's for those of you that are interested. But as I said, since we kind of strayed away from the very advanced mathematical framework, we didn't use that in our treatment, but this is the mathematical basis for this. And the main idea, the big idea behind this framework is to promote the Cartan calculus that we have on space-time to field space. And this will allow us to have a symplectic structure directly on phase space, on field space, excuse me. And that will then allow us to treat things like charges, symmetries, Noether theorems, without ever choosing coordinates on the space-time. So that's where the covariant comes from. So let me just quickly, also to fix notation, say what I mean by the Cartan calculus on space-time. It's this set of three operations that we have on, so we have the space-time manifold, and we have the set of all forms on this manifold, and then we have these three derivations here, the exterior derivative, the interior product, and the Lie derivative that have a difference, that act on the forms and change the rank of the forms in a different way. So the set of these three operations, together with these relations between these operations, and in particular, the last formula here is known as Cartan magic formula. And this set of three operations and this relation between them is what I call Cartan calculus on space-time. So what we want to do is to have this notion on field space. So the first thing that I will do is say what I mean by field space. And I will here quite simply say that field space is just a set of all possible configuration of the fields. So here A is any index of the field. So it could be a spacetime index if you have vector fields. It could be a color index. It could be anything. And the X is just spacetime points. And you can think of these field configurations as coordinates in this infinite dimensional manifold. So then, very naturally, you can define tangent vector to this manifold in this way, where you can see that this is a straightforward generalization of the finite dimensional case. So instead of having the usual partial derivative as the basis for this vector space, you have here the functional derivative, then you sum over all A's and you sum over all X, and this will give you a general vector on field space. So in particular, we're going to be very interested in vectors in field space that arise from a gauge symmetry. So let me say what I mean. Given a gauge transformation, so this epsilon is a gauge generator, so it's part of the Lie algebra of the gauge group. You can form a vector on field space basically by saying that the components of this vector are going to be the gauge transformation of the infinitesimal gauge transformation of the fields, right? So this is pretty straightforward. This is the type of vectors that we're going to be interested in. And as a concrete example, say you are talking about diffeomorphisms as gauge transformations. So in this case, you can take epsilon to be simply a vector in the space-time. And then the corresponding vector in field space is going to be the one with the components given by the Lie derivative, the space-time Lie derivative of the fields here. So in the following, every time we're going to see this kind of V as a vector in field space, is going to be implicitly a vector that's generated by a gauge transformation in that way, right? So now that we have manifold in vectors, we can start defining these operations. For example, we can define the external derivative in a very simple way that we define it on the coordinate function, as you would do for spacetime, and we say that they are simply the duals of this vector basis here. Then once we have that, we can define the integral product, which basically is going to, again, very similarly to the spacetime case, when you act with these vectors that we talked about on the basis one form in this field space, you just pick up the components of the vector, right? So once you have that, you can generalize this straightforwardly to forms of any degree, and then you can define this, finally, the Lie derivative through Cartan's magic formula, and then you have these three derivations on the field space, the set of all differential forms on field space that obey these relations there. So you have the Cartan calculus on field space. So now that we have that, we can start using it to talk about theories, in particular in the Lagrangian formalism. Now in our language, the Lagrangian here is going to be a four form on spacetime. Obviously, it's a top form on spacetime, but it's also a zero form on field space, right? Since it's a function of fields, just a function of fields, it's going to be a zero form on field space. And then once you consider the variation here, you can always put the variation of the Lagrangian in this form here on the right, where you have the equation of motions that multiply the variation of the field. And then you have this boundary term, right? When you calculate the variation, you're always going to be doing integration by parts. And all of these terms you integrate by part are going to be put in this boundary term here with this theta here. And now you can see easily that this theta is going to be a three form on spacetime because there's this d, it's a boundary term. And also it's going to depend now on the variation of the fields as well as the fields. So it's now going to be one form on field space, right? Now what you can do with this theta, so this boundary term is going to encode all of the information of the symplectic structure of the theory. So once you have the theta, you can integrate it on a sigma here, a Cauchy surface. This technically has to be a submanifold of Cauchy surface, but I won't go into these details right now. You can think of sigma as just a Cauchy surface. So if you integrate this theta, you get this presymplectic potential big theta here. So now that you've done the integration, this big theta is going to be a zero form of spacetime because you did the integration, and it's still one form on field space. So now that you have a one form on field space, a pure one form on field space, that's not a form on spacetime, you can just take its exterior derivative that we defined earlier, and you get a two form on field space that is closed. It's obviously closed because it's exact here, right? So this omega, this two-form on field space that is closed, we're going to call the presymplectic form. And that's how you get the symplectic form in your theory. Now, why is it called the presymplectic form and not, why do we have the pre here? Well, simply because, yes, this form is closed, but it's in general not non-degenerate. You know that to have a symplectic form, you need it to be non-degenerate. And in our case, sigma omega can in general be degenerates. For example, in gauge theories, without boundaries, like forget about boundaries for time, this omega is still going to be degenerate in the gauge directions. We're going to see it later on as a result of Noether theorems. So what this says is that this field space F can always be made into a Poisson manifold, for those of you who like the technical things, but it's not yet symplectic. So we don't really have a phase space yet. So the way to usually get a phase space is to just do the symplectic reduction, and you gauge reduced your field space here. So you have this F tilde that's just the field space, but you quotient out the gauge directions, and this gives you then a symplectic manifold here, because the form omega tilde that you have on this manifold here is going to be non-degenerate, because you killed all of the directions in which it was degenerate, the gauge directions, right? And then the important thing is also that this form omega tilde that you have here is going to be such that, so you have an obvious projection from this space to this one, the quotient space, so you can pull back forms here to this one, and this symplectic reduction is made in such a way that this omega tilde form is going to be the pullback of the presymplectic form to F, right? So that's the symplectic reduction story. And a very important point that's going to be very important for us later on is that, yes, I stopped a bit because, yes, that's what I meant. It's pullback, yeah. Omega is the pullback of omega tilde. Maybe I misspoke, I'm sorry, yeah. But on F, yeah, no, okay. Yeah, that's the thing, right? Projection goes this way, so the pullback goes. Yeah, okay, well, projection goes this way, so pullback goes this way. Okay, that works. Thank you. So the very important thing is that this presymplectic form that we had, that is degenerate, we need it to be degenerate to be able to perform the symplectic reduction, as I told you. For then in the end, for this form to be the pullback of the tilde form, because otherwise you have directions that are not encoded in this form, right? If it's not degenerate, you can't assure that the omega tilde is going to be pulled back to this form. This is explained quite well in this work from Jankovic and Witten, where they talk about the covariant description of basically gauge theories. And in some ways, our work is a generalization of this paper in the presence of space-time boundaries. So this is something to remember. We need this omega form to be degenerate in order to perform the symplectic reduction and get this physical non-degenerate omega tilde form. Okay? All right. Yeah, so now how are Noether theorems and charges in this language that we developed? So if you take any symmetry that's described by a vector in field space, so you have this vector that's basically in the direction of the symmetry of your theory, and you contract it with this presymplectic form, you will get the exact differential of a function here that we call the charge. And the very important thing is that this is always going to be on shell. This is true only on shell, and every time we talk about charges and that kind of stuff, it's always going to be assumed that we are on shell, so on the solutions of the equation of motion. And this is the usual equation of symplectic geometry, just now in our field space. So it's kind of a generalization to infinite dimensional manifolds. But this is the normal Hamilton's equation, I think they are called, in symplectic geometry. So this is just a result. And then Noether theorem comes in as in two parts. The first part is that if this T is just internal. So that means that this vector does not come, this vector in field space does not come from a gauge transformation. Then you have that this charge is simply given by the integral of these currents, and you have the current given here in terms of this theta that we've been talking about earlier. So that's nice. But more interesting for us is that if you take, instead of this general internal T vector, you take this V vector that we talked about. Oops, sorry. Okay. That is a field space vector generated by a gauge symmetry, where then you see that this charge is given by the integral of an exact form. So what happens is that then Stokes' theorem can just go to the boundary. And that's why if you have no boundaries, if you just you have a gauge theory with no boundaries, this charge is going to be zero, right? If you have no boundaries, this is just zero. And this is what I meant by the fact that the symplectic form, the presymplectic form, is going to be degenerate in gauge theories without boundaries, because then you have that the contraction with V here is going to give you zero, and that's the degeneracy of the symplectic form in the gauge directions, right? But if you have boundaries, well, then this is going to give you a surface charge, right? We call this a surface charge because it's on the boundaries. And that shows you that in gauge theories, it's the main reason why in gauge theories, the presence of space-time boundaries changes things and is very interesting. In some ways, the fact that the gauge symmetry usually gives you a vanishing charge is what we mean by saying that the gauge symmetry is not physical, because it doesn't have a charge associated to it. But in the case of boundaries, you can see that there is a charge. And so in some sense, this gauge symmetry becomes physical. And that's going to be very important for the following.
So perhaps gauge symmetry, what is gauge symmetry in bulk is the physical symmetry of boundaries.
Yes, yes, that's exactly it. So it becomes physical on the boundaries, exactly. And this is going to, yeah, and we see how this is very important for what we're doing. So yeah,
it's important that that if we contract in T with symplectic form, we get the exact variation of H, because if H is not exact, then if we want to get H, then we integrate over T in the field space, and this is path dependent, or am I right? Or?
So there's no integration in field space. I'm not sure what you mean by that, but
Suppose like you wrote that delta H is like a total
yes,
variation of some function and this function of this, and there could be some T for which
yes,
this delta H is like it's still a 0-1 form, but it's not
it's not exact. So this is actually going to happen in gravity, that we here do not have an exact term. This is going to be important as well for the edge modes.
Do you mean this? You mean this is definition of symmetry?
Well, I would say this is the definition of what symmetry is.
Okay, but
I think it can be. Yeah.
But then it's true only without boundaries, so we don't have definition of symmetry when we consider theory of boundaries.
Well, this point is true also with, like, here it's also going to be true even if there's boundaries. It's also going to be the total differential of a H charge, yeah, even with boundaries.
So my understanding is, but perhaps I'm wrong, that this is what is in in this frameworks is a definition of what the symmetry is.
Yeah.
And then this function H, this Hamiltonian, can have different forms. Might be a total differential, in which case it signals that we have to do with gauge symmetries, or it cannot be, in which case we have to do with something like global symmetries or something. Yeah. And they are actually subject of first and second measure theory. That would be my understanding.
That's also, I would say, because this is just saying that this T is a Hamiltonian vector field, right? So in the symplectic geometry, I think this is a good definition of what we mean by symmetry. Okay, so let us now apply all of this, and it's going to, I think, be also clearer when we take an example, and we're going to start with Yang-Mills theory. So Yang-Mills theory just take the usual Yang-Mills action here. And so what do? You take the variation of this action, and you get the equation of motion on one side, and then all of the boundary terms that you often forget about is going to be the thing that interests us, is given here by this omega right here. Right? Omega is going to depend on A through this F here and on delta A. So now the procedure that I presented before is going to, the first thing we have to do is we integrate this over sigma, and then we take this exterior derivative, field space exterior derivative, and we finally get this presymplectic form of Yang-Mills theory in this very nice form here. Right? So the first thing that I want to note here is that if you consider a gauge transformation, so just a Yang-Mills gauge transformation on A, you can see that the entire symplectic structure is gauge invariance. If you consider gauge transformation that are field space, gauge transformation that do not depend on the field, right? Field independent gauge transformation, which is what you usually do. So if this gauge transformation has nothing to do with the field, then the structure is completely gauge invariance. And this is the first main difference with the work of Varrin and Friedel, because in their work, they say, we consider gauge transformation that can depend on the field, and then we show that the symplectic structure is not gauge invariant. And then they say we have to introduce edge modes in order for the symplectic structure to be gauge invariant. But this is actually not necessary. You can consider just normal gauge transformation that do not depend on the field. You have this structure that is gauge invariant, and the edge modes are going to arise from a different condition that we're going to see very, very, very soon. But that's the first very important thing to note, is that the structure is gauge invariant. So now we want to calculate the charges, right? So what do we have to do? We have to take the contraction so this vector V now is going to be the vector whose components in field space are the gauge, the SUN transformed fields. So you can form it easily. Then you take the contraction of this form that I showed earlier, and you indeed find, as you would expect, a surface charge, so a charge that only has support on the boundary here, and that is actually a complete differential here of this Yang-Mills charge, and the Yang-Mills charge is simply given here by this formula, right? So that's nice. We have now this Yang-Mills charge on the boundary, but what this also implies is that this presymplectic form is now non-degenerate, right? Because now in the gauge direction, this contraction gives you the charge, and it's not vanishing in general. So that means that this is now non-degenerate, and you can't do the symplectic reduction that we usually want to do. And you can't have this condition that then this omega tilde is going to pull back to this omega and everything we talked about. Remember, I told you that this degeneracy condition was a very important one for the symplectic reduction. So how do we fix that? How do we still want to go through our usual symplectic reduction? Well, this is in our formalism, this is how the edge modes are going to be introduced. And I call them here the gauge edge modes, because as we're going to see later, for gravity, there's different types of edge modes. But for now, this is like the reason that the edge modes are going to be introduced. A question? Okay. All right, so how do you do that? Well, you define this field phi on the boundary that takes value in the group, in the gauge group, so SUN in this case, that transforms in this way. And so this is the finite transformation. This is the infinitesimal version of the transformation. And if you have this field transforming in this way, you can add.
So G is a function.
AG is just a gauge transformation, sorry.
Yeah, but this is a group value function, for example. Yeah.
Phi.
It's a group
Yeah.
value function on the
Group value function on the boundary, exactly.
Okay.
I mean, that's.
Okay, so what is gauge transformation? I or G?
G is a gauge transformation.
Phi.
Phi is this edge mode that is a group valued function on the boundary.
Okay, but what about G? G is not point value. Is
Okay.
it point dependent?
So
It's-
essentially the idea is that you add an additional scalar field group values or algebra values, group value, right?
Group value, yeah.
Scalar field. I mean, the connection is the algebra values, vector, right? And on the boundary, you have the group value scalar field, which transforms on the gauge transformation in this way. Okay, G is a gauge group element.
And you don't allow transformations, local gauge transformations, such that J is G is a function.
That's what it is. It is.
It is.
It is.
Okay.
So this is just a group element of the gauge transformation.
Mhm.
So you are on the boundary now, you have two sets of fields, one is the original gauge field, another is the scalar field. Then you want to know how then you assume that the scalar field also transforms the gauge. And the essential idea is that you introduce it, you have to kill the charge.
Yep,
So
that's going.
complete charge of this. So guys is zero, so the symplectic actually becomes degenerate again.
You're spoiling the result, but yes.
So you can think of this, so if you have a big surface, kind of spherical surface in electromagnetism, you have some charges inside,
What?
right? Then there is a charge, or if there is a pure electromagnetism, there is certainly this charge you can measure on the surface, right? I mean, by Gauss law, you essentially know that some components of electric fields has some particular properties which is related to the charge on the bulb, right? And this follows this property of symplectic structure that we want to preserve. So now you are on the same surface, you add some additional charge just to compensate for the charge which is in the bulb.
Yeah,
Okay,
so
so that's basically it.
let me just get, because the next slide is basically what you're saying. So, but so that's what. So now you have this field on the boundary, this additional field that you add to the field space, right, to the content of the field space. Then you can add to the symplectic structure a term of this form, right here. And now you see, then you take the variation and you have this symplectic form of this field phi. That now depends on the field, the gauge field A, but also on this additional field phi. And you have this additional structure to the symplectic form. Then you add the one that we had before to the one we have now, and you have this total symplectic form here that depends on all of the fields. And now, once you take the contraction with this gauge, this field space vector that comes from the gauge transformation, as Ludovic said, now we have a vanishing charge. So that's exactly the point, is that you can, so once you have space-time boundaries in your gauge theory, you have charge appearing on the boundaries, but you can also kill those charges by introducing edge modes, so fields on this boundary that act in a way such that the charge is actually vanishing. Right? And now that we have this condition, we now once again have that the symplectic form, this total symplectic form here, is degenerate in the gauge direction. Now we can just go ahead and with the usual symplectic reduction, the gauge reduction, and you can now do exactly what we've been saying about. In the field space, the phase space, that now contains also this gauge edge mode, this phi here. All right? So that's the way we introduce edge modes in our treatment of the thing. And that's basically the idea for Yang-Mills. So now let's move on to gravity. Gravity, so yeah, let's go step by step. So we just take the usual Einstein-Hilbert action here. So now G is the metric. It's not the gauge transformation anymore. It's just the metric, so right? It's the field of our theories. And you do, again, the same thing. So you take the variation, and you will get the equation of motions, Einstein's equation in vacuum, and this symplectic. So this is the pre-symplectic potential current, but it's the theta that we've been talking about. And note here that it depends on the metric and on this variation of the metric. Here is just a nice form to put it that way, but obviously the connection here is just the derivative one. So this is also a delta of the metric, right? So now that you have that, you do, again, the same thing. You want to integrate this theta, integrate it, and then take the variation, and you get this symplectic form for the Einstein-Hilbert theory. Once again, here it's very obvious to see that this symplectic structure is completely gauge invariant, right? So here the gauge transformation are diffeomorphisms. It is completely gauge invariant because there's no index, right? Everything is contracted. as long as you consider, again, non-field dependent transformations. And in Donnelly and Feder paper, in the gravity case, they do the same. They say, if you have gauge-dependent diffeomorphism, field-dependent diffeomorphism, so diffeomorphism that depend on the metric, this structure is not gauge invariant anymore, and you have to add the edge modes. But in our treatment, you just consider normal diffeomorphisms. This is completely diffeomorphisms invariance, right? So now, once again, we're going to do the same thing. We're going to say, let us form this vector here, right? That's the vector formed from the gauge transformation of the fields. So the gauge transformation now is just a space-time derivative, and you take the contraction. And now here's the big difference. The first big difference is that, as we've been saying, this contraction here gives you this exact form, but there's also this flux term here. Now, this flux term arises, so basically this flux term expresses the fact that the system is dissipative, and it arises because we are not considering gauge transformations, so the diffeomorphisms here, that potentially move the boundaries, right? Before the SUN gauge transformation, they had nothing to do with the boundary in space-time, right? But here, diffeomorphisms can move the boundaries, and this is why we have this flux term appearing here. So in the case of gravity, so let us first consider, you can see in the previous formula that if you take diffeomorphisms that are boundary preserving, so imagine diffeomorphisms that are tangent to the boundary. So you can see in this formula here, if you take epsilon to be tangent to the boundary, this term vanishes, right? And then for those kind of diffeomorphisms, you have that you don't have the flux, and you have the usual formula with the exact form, and you have this charge here in gravity. And this is what we call the Komar charge. It's a very famous charge that we have here. But this is, at this point, only valid for boundary preserving diffeomorphisms. All right? So what do we have to do in gravity? What problems do we have? Well, the first one is what I've been talking about, is that we have this flux term. The contraction is not a complete differential. And I didn't have time to get into it, but this also happens in Yang-Mills theory, for example, in electromagnetism, when you consider global Poincare symmetries. Right? Like Maxwell's theory is obviously also invariant in the global space-time symmetries. And once you consider that, and it's in the paper that I showed at the beginning, you also have fluxes, because the global space-time symmetry will also change the location of the boundary. So you can also have these kind of fluxes in Yang-Mills theory. But here in gravity, we have these diffeomorphisms that potentially move the boundary that will spoil what we call the integrability of the charge. Basically, it's just saying that this contraction is not giving you a total derivative, a total differential. So that's the first thing we want to deal with. But then we still have the same issue that we had with Yang-Mills, that even if we do not have this flux, we still have that this contraction gives you something that's non-zero, this Komar charge that we've seen. And so this symplectic form is non-degenerate, and we can't perform the symplectic reduction as we would like to do. So there are these two issues to deal with. So if we start with the first one, the flux problem, this basically arises because in all of the calculations we've been doing, if you remember how I defined the symplectic form at the beginning as well, we basically assume that the variation of an integral is the same thing as the integral of the variation. We just commuted the two without thinking about it. But you can understand that if the integration here is of a sigma, and this variation, when you contract it with a certain symmetry, with a certain vector and field space, also changes the location of sigma here, well, you can't just put it inside and not worry about it, because the integral limits, the bounds of the integral is also going to change in this variation. So this is only true for boundary preserving variations and symmetries. So the solution of that is to be very careful about the embedding of the sigma into the manifold and look at how that can also vary. And this is what we're going to do for gravities. Now we consider this space-time embedding, this version of phi here, that just goes in from this parameter space to the manifold. That says how it's just, yeah, it's just the parameter space into the manifold is the embedding. And note here that I will denote by this kind of x is the values in this parameter space, and then the x that we have been using until now is just a point in space-time. And we now consider a subregion of M that is parameterized by this R here. So you have this R that parameterizes this subregion R non-calligraphic in M. And now you consider the action, the gravitational action on this subregion R, right? So now you just say, you integrate the pullback of this Lagrangian, right? So this is what we usually do, but now we are very careful about keeping track of the embedding, like being explicit about what happens with the embedding. And now this action is going to depend on the fields, but also on this embedding field here. And if you just wanted to write the integral out, you integrate over this parameter space here, and you have here the Jacobian, right? And then L is going to be evaluated at the phi of x. So this is the action in a way that you keep explicit track of this embedding map phi.
I think it's important here what actually this boundary is. What is your definition of theory on this boundary?
So
I mean, there can be two boundaries. We can consider our classroom as bounded system. However,
sure.
it's not really a boundary because we have the world also.
Yes.
So we just separated part of. On the other hand, there may be a physical boundary, like
Yeah.
if there is some conditions satisfied by
So
such a boundary, and then literally there is nothing.
yes, so I think here it's simpler to, especially for gravity, it's simpler to imagine that we consider a subsystem, right? We consider a subregion of space-time, and then the subregion is going to have a boundary. Well, that was the main idea of the paper by Fredel and Donnelly. Is to, I mean, the title is local subsystem.
Fields on boundary.
No.
There's no boundary conditions. No. And so this R is actually going to be the subregion of space-time that we want to consider. And this whole ideas about edge model and stuff is to be able to consider local subsystems of gauge theories, right? That was the work from Fredel and Donnelly. So but that's a good point, thank you. So this R now is going to be, imagine you take a subregion of space-time R, and you want to do gravity in that, or any, for now, this is for any theory, right? As I said, this can also be used in Yang-Mills theory to kill the fluxes of the global space-time symmetry. So, but you consider this subregion R, and then this subregion is going to have boundaries, right? We're going to see it. So yes. Now you have to be very careful, and there's a lot of calculation in the paper about that. But now you want to calculate the variation of the action that I showed you, but you have to be careful because you're going to have this phi as well, and you have to understand how you compute variation of embedded actions and how this embedding is going to also give you additional terms with the variation. But in the end, it's going to give you a very nice form where if you just define this chi field in this way, you can write the variation of an embedded action. And again, this is completely general. In the same way, so you can see here that we have the equation of motions times the variation of the field. This is the usual thing you have. You have this boundary term that we call theta. So this first part here is exactly what we had before, except we have we are keeping track of the embedding here, right? But then this variation, because of the embedding that can also vary, is going to give you an additional term here. It's given by this Lie derivative with respect to the vector field we define here. And it turns out that this is actually a total divergence. So this is very good because it means that it's not going to affect the equation of motion, which is nice, but it's going to affect the symplectic structure, right? Since the symplectic structure was given in terms of the boundary of this variation, well, then this term is just going to modify the symplectic structure, and that's what we wanted, without touching the equations of motion in the bulk, which is very important. So, right, and then you can define this extended. So this is called the extended phase space formalism because you add this embedding as a dynamical variable to your phase space, your field space, and now we can have this extended symplectic potential here that's simply given. So as before, like you just integrate this over a sigma, and now this S is the boundary of R, right? This S is just the boundary of the R that we had before, and this extended symplectic structure now has this term that we already had before, that was the definition, but now you also have this additional term here, right? So now you want the form, so you take the variation of that. Okay, this is the same, take the variation, and you get this, this symplectic form, where again, you can see that we have the same thing we had before. This omega is just the delta of theta, the normal theta that we had before, the same one. So we have the symplectic form we had before, but you have an additional boundary term here that depends explicitly on this chi field that we've defined before. Chi is just defined through phi. So chi is just an expression of this embedding, the variation of the embedding. So you have this entire additional boundary. Yes, so S, yes. Yes, R. So R was the manifold, the entire manifold. S was like the Cauchy surface of that manifold in this parameter space, and now the boundary of S is similar to the boundary of sigma, right? So you have this entire additional boundary term to the symplectic structure. So this is for any theory. This is very general for now. But if you apply it to gravity, you're going to have some kind of simplification, because in gravity, the Lagrangian on shell is 0. So if you look at gravity and you do the exact same thing, you will find that you have this for Einstein-Hilbert, this extended symplectic form that now depends on the metric, but also on this dynamical embedding field. And you have the same thing as before, and this additional boundary term here, where you can see that the term that dependent on the Lagrangian just vanishes because we are on shell. And in gravity, the Lagrangian vanishes on shell.
Right, but it only holds in the field gravity without matter, right? Because
Yes, so yes, the Einstein-Hilbert vacuum, the theory that we've been doing before, of course.
But if we added to this Young-Mills field, then we could add also the edge mode for Young-Mills, and those terms would simply add, or there would be something more?
So if you add Young-Mills, just minimally coupled.
then there's going to be, first of all, the Young-Mills charges are different kind of charges, right? Because this charges here are such a thing.
Yeah,
But of course, there will be all of them, right? All of them will be.
All of it, yes. But
it will be just a sum of terms.
Well, usually the gauge charge is not called for all these charges.
it should be independent, right? Yes, but also I want to note here that this phi that we also call an edge mode is for now very different from the one we had in Young-Mills, because the one we had in Young-Mills was to restore this degeneracy condition, right? This one for now is only to deal with the fluxes. So you could also add this one to Young-Mills theory to kill the fluxes of global space-time symmetries. Okay, so now if we compute the charge of this symplectic form, right? So you do the same, you compute this contraction with this vector. Now you find that this is actually the variation of this full thing, which is actually the coma charge that we had before. So you can see now that, and this is valid for any diffeomorphisms, right? So even if you have diffeomorphisms that are not tangent to the boundary, you get that this contraction is a total differential. So if you add this embedding as a dynamical field to your theory, then the charges do not have flux anymore. You don't have the flux term here, right? So that doesn't mean the system is still dissipative, right? But now the flux, the information of the flux is encoded in this phi edge mode here, right? So as before we had that the information of the charge was encoded in the gauge edge mode in Young-Mills. Now the information of the flux is encoded in this space-time edge mode phi, right? So this is the first result. And it's a note also here that it's very important that this delta here is before the integral, because if you just put the delta here, it's not going to be the same expression, right? Because now we know that this is going to change also with respect to delta. So that was the whole point of keeping track of this amending. Okay, right. So now we still have, yeah, so that's just a recap. So that's just what I've been saying from before, right? You had this embedding.
So we I thought we defined some subsystem, and then in addition to the fundamental fields, suddenly we postulate the existence of new fields on
the boundary.
the boundary.
Yeah, so I think it's just for me it's just two different ways of seeing the thing. Like you have your system with the boundary, and you have possible fluxes through this boundary, and you can describe it like that. We can also describe it instead of having those fluxes by simply having those fields on the boundary. It's similar to before. I think it's just two different ways of looking at the same thing. The same information physically is there. Yeah, you could have like exactly. You could have like radiation. Yeah.
Maybe it can be said in another language that to get some charges, we really calculate those charges, the difference between the charges and the charges of vacuum, so which are 0, and then these modes like so we showed some vacuum. So these modes are like closed on bosons of elliptical and me. Or there is this language totally.
I don't want to make any statement about that. I wouldn't know. Maybe that's we've not thought about that, so I don't want to say yes or no. But please try it out and see if it's equivalent. Right. Okay. And also the thing that I've stressed since the beginning is that this edge mode that we have now in gravity is very different for now to the edge mode we had in Yang-Mills, because they serve very different purpose. However, now what we still have to do is that we still have this non-degeneracy here that we want to fix. Yes. Again, I'm a bit quicker. So we still want to fix this non-degeneracy, and turns out that, remember in Yang-Mills we added a term to the symplectic structure. It turns out that in gravity you can add this term that you want to add to the symplectic structure is actually also going to be given in terms of the same embedding edge mode. So you can see here that the term you add to the symplectic structure of gravity is given in terms of these embedding fields here, right? You add this term, then the total symplectic form is given by the extended form. So that means the symplectic form we had in the extended formalism with the embedding keeping track of, plus this additional term that we just written here. And now when you take the contraction, not only you don't have fluxes because this deals with fluxes, but you also don't have the charge because this additional term just kills the charge, right? So you have the same story that now this edge mode, this phi edge mode is taking care of the charge, and you have a vanishing charge, so you can go ahead with the symplectic rotation and everything. But in gravity, it turns out that this edge mode that deals with the flux and the edge mode that deals with the charge are actually the same field, this embedding field. And so that's the story in gravity. Yeah, so that's just a recap. So you first extend it, so you have the flux here. You extend it by keeping track of the embedding such that the flux disappear. And then you add this additional structure to the symplectic form such that the charge disappears. And now you can construct the physical phase space by removing the gauge directions, as we like to do in symplectic reductions. And that's it. That's another just the things I've been talking about since the beginning. So there are two types of edge modes: the gauge edge modes and that deal with the degeneracy of the form, and the spacetime edge modes that deal with the fluxes. When gravity it happens to be the same, basically because the gauge group of gravity is the diffeomorphism. So you can see it as coordinates on the manifold. And yeah, that's it. So I guess we still have time for some questions. Thank you.
Next question is.
Yeah, so do you know the paper by Cardero and Villas Senior?
About, do you know like the title?
I think I don't remember the title, but they wrote a paper on theories on boundaries, and the conclusion seems to be the same, that they consider theory is everything consists of the bulk term and boundary term. So, so maybe okay. The difference is that in their case they actually don't discover the problem. They immediately propose a solution. So they propose that action consists of bulk action and boundary action, and then they have all those variations of big bulk and boundary. Maybe 2 or 3 years old. They gave a lecture on this in Author, which was 2021.
That's interesting. Okay.
I will send you.
Yeah, please do. Yeah.
Yeah, so maybe the framework is a bit, yeah, but maybe it's similar.
Kind of the same, yeah.
Anyway, they're studying. And I have one more question. So you mentioned earlier those charges defined by Fourier-Mills theory. So at the end of the day, you just kill them.
Yes. Well, we put them in the edge modes, right? That's what I've been saying, is that instead of having those, no, still gravity, instead of having those Yang-Mills charges, non-vanishing surface charges, that's what Jurek was saying as well. If you imagine in electromagnetism, instead of having this boundary, this sphere, and the charges on the sphere, you can consider equivalently fields, edge modes on this sphere that acts in such a way that they kill the charges. That's the main idea.
So at the end of the day, we don't have anymore, we don't have mass or momentum. This is all zero after your selection.
Well, I think like it's an equivalent framework, so it doesn't mean that you don't have. So you mean, for example, the Komar charge in Schwarzschild, right? Where it's just the mass of the black hole. I have.
Comment about Komar. I mean about your the way you call it. So actually, Komar is usually referred to the case when a specific state has symmetry, and then this transformation actually is preserves the state, literally preserves the state.
Okay.
So when psi is killing vector, not only
Oh, so there's for specific default.
Yeah, well, it's just, yeah.
I would say for specific. So for specific.
Yeah, I understand. For given solution specific default.
Well, that's, yeah. For example, here.
Well, so that means that so really refers to particular solution.
Yeah, I understand that it refers to solutions, but there is a subclass of solutions.
Yeah.
which
Okay.
can be very short,
Yeah,
right?
yes.
So the big solutions,
Yeah.
vectors, Komar usually tries to those.
So
But they're probably allowed to use his name. I don't know what.
I didn't ask him, but
No, the expression is the same, right?
Yeah, the expression is this.
yeah, and it does reduce to what we usually call the Komar charge when you do consider specific solutions. So I think that's why we use that name. Yeah.
But there is difference between nether charge and Komar charge. So nether charge defined for arbitrary, for arbitrary spacetime, not necessarily eliminating the given vector. While Komar, he defined its charge only for spacetimes which admit killing vector. This charge was for this killing vector. And so this is historical.
Yeah, I guess there's maybe a subtle difference. Okay, other questions?
Okay, if there are no questions, we'll close out. Exactly on time. Thank you very much. I have seminar next week, but Wojtek probably knows, so perhaps Jacek knows. Say that again. Who's gonna give a seminar next week? Me. Oh, yeah. Okay, so
So I would like to